Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a theoretical physicist currently working as a university researcher over in the Helsinki Institute of Physics in the University of Helsinki in Finland. And I'm a cosmologist, which means that I study the universe, the contents of the universe. Sorry, one sec. Just had a cat walk across my keyboard and open up a bunch of things. That's why I turn off my keyboard. As I was saying, I'm a cosmologist, which means I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. It's a really fun topic. I love being a cosmologist, and I love chatting to everybody about all of the cool things I get to work on. So for anyone who doesn't know, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want about space, about physics, about academia, about myself, about Finland, about the cats that just walked on my keyboard. You can ask me anything you want, and I will do my best to try to answer these questions. As always, I might not have all of the answers, but I will do my best to answer whatever questions you can come up with. For anyone who's a first-time viewer, welcome. For anyone who's a regular, welcome back. It is great to see some of the regulars already here in the chat. I see we have Scott, Prath, and Nina, Ben. Welcome back, everyone. It has been a while. It has indeed been a while since the last Cup of Cosmology. I think coming up to 4 months, might even be just over 4 months by now. Yeah, life got busy. As always, Cup of Cosmology is something I love doing, but it is something that I never want Cup of Cosmology to be a mental load for me. And back in end of autumn, I felt like it was. I had too much going on. I needed to take a break. So that's why there has been no Cup of Cosmology for the last 4 months. But I'm very happy to come back and chat to you all about physics and space and all of the cool stuff that has been happening and the cool stuff that I've been up to. So thank you everyone for coming back after the 4 months hiatus. It's great to see all of you coming back in again. And as always, please do all of the usual YouTube stuff. There's buttons you can press. You can subscribe. You can click a notification bell. You can like the stream. You can leave a comment. You can also do a bunch of stuff on Twitch, but I think there's like one of you watching on Twitch and everyone else on YouTube. But if you're on Twitch, press buttons too, see what happens. I don't know what buttons do what on Twitch, but press buttons, see what happens. It's always a fun thing to do. Okay, so I see comments already saying cats complicate things. Yes, they do indeed. Cats are lovely. But cats on keyboard is always a fun mix. Usually, as soon as I start the stream, I turn off the keyboard to prevent exactly what happened. I didn't do that in time, so I started talking and suddenly I had a cat blocking the screen and stuff popping up on the screen, which is why I've immediately turned off the keyboard now. Cats, fun little creatures to have around. Okay, I see the comment from Prathia, life is normal again. Indeed, everything is back to normal. Cup of Cosmology is back. You get your weekly dose of science. So, as usual, this is an interactive stream, which means it's up to you all to ask questions, and based on that, we figure out which direction we take this stream in. So that means that you get to decide what we talk about. As always, if you don't ask questions, I get to talk about my favorite things, which is probably going to involve the beach ball behind me, dark matter, gravitational waves, and fun things like that. But I see we have some comments already, some questions already, and I can actually answer 2 of the questions together. So there was the question from Ange of what has happened in physics since my last stream. Not much. We haven't found dark matter. We haven't, revolutionized physics. We haven't thrown out gravity just yet. We haven't discovered quantum gravity, but there have been some cool things happening. And there's a question from Ben of, is there anything new from DESI? DESI, as a reminder, is a dark energy spectroscopic instrument. It is a ground-based telescope that is mapping the night sky and trying to help us understand dark energy. I'm going to do a quick recap of what dark matter, dark energy, things like that are before I answer those 2 questions. Short answer is nothing new from DESI, but there is something new from a related experiment, and it's going to tie into DESI results. So let's just set the scene, because it's been 4 months, and if I take a 4-month break, I forget everything that I knew. So I'm going to assume that you've all forgotten everything I've ever talked about on this stream to some degree. So I'm going to do a quick recap, and then I'm going to answer the question of DESI related results and what else is new since my last stream, which was 4 months ago. Rumor has it the grand unified theory has been solved and will be revealed in this show. Not today, unfortunately. Maybe someday. If the day it is solved, you can be sure Cup of Cosmology will talk about it. But let's see when that will be. Okay, let's do a quick recap of some things. And I want to bring up my slides, and it's going to open on the slide, which is not the slide I want to talk about, but it always just takes a minute for my slides to load ever since Restream updated things some months ago. Okay, quick recap. What is the universe made of? Great question. The universe has three main components. Everything we see, everything we're accustomed to, everything from me to my cats to my very hot tea to the stars you see in the night sky. All of this is normal matter. Now, normal matter only accounts for 5% of the energy budget of the observable universe. There is another 26%, 26.2% in the form of dark matter. Dark matter is this weird type of matter that that interacts gravitationally, but does not interact electromagnetically. So it is essentially invisible. We cannot see dark matter because it does not emit light, it does not reflect light, it doesn't do anything with light, and therefore we cannot see dark matter. But we know it's there because it interacts gravitationally, and without dark matter, the universe would look very different. The remaining 69% of the energy content of the observable universe is in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe. It's pushing everything out from everything else. And that is pretty much everything we know about dark energy. In our standard model of cosmology, dark energy is what we call a cosmological constant, which means it is constant in time. The way dark energy behaves today is the same as the way the dark energy would have behaved in the early universe. This is what we have in our standard model of cosmology, known as lambda CDM, lambda being the dark energy component, CDM being the cold dark matter component. Where do all these numbers come from? How do we know that 26% of the universe is dark matter and 69% dark energy? Well, we know this from the cosmic microwave background radiation. It took less than 10 minutes today. Cosmic microwave background radiation, CMB for short. This is a map or a picture of what the universe looked like 380,000 years after the end of inflation, or almost 14 billion years ago from our perspective. In the very early universe, there were three main components. There was photons, which are particles of light, protons, and electrons. Initially, all three of these were bumping into each other. Dark matter was off doing its own thing. So initially, all three of these were bumping into each other. As the universe gradually cooled down, the protons and the electrons could combine together to form the first atoms in the universe. At this point, the photons, the particles of light, could no longer interact, and so they broke away. They have been traveling freely ever since, and today they make up this cosmic microwave background radiation, this background light that is behind everything else in the universe. By looking at the temperature or the energy of these photons, you can see we have the bluer ones, which are slightly colder, the orange ones, which are slightly hotter, more energetic. By looking at this, we can understand what the universe is made of. This image here is known as the Holy Grail of cosmology, or to some of us, like the 10 people who call it that. But the cosmic microwave background radiation tells us that the universe has 5% normal matter, 25% dark matter, 70% dark energy. It tells us the age of the universe, which is about 14 billion years. It tells us when the first stars turned on, we think. It tells us what the universe looked like at the end of inflation. So this map here gives us these values of 5% normal matter, 25% dark matter, and so on. Just to make it clear what we're talking about here, this cosmic microwave background radiation is in fact a sphere around us. We live at the center. This is basically the same thing, just this is on a sphere. The version I was showing you just now is projected into a 2D surface, but we live at the center of this. This is our observable universe, so it is the furthest we can see in every direction we look. Just to clarify here, I'm not saying we are the center of the universe, but we are the center of our observable universe, and this is the boundary of our observable universe. And I love my beach ball. Got to show off my CMB beach ball. It is necessary. Okay, so that's the recap. We have three main components in the universe today. We know their quantities thanks to the cosmic microwave background radiation. 5% normal matter, 25% dark energy, 25% dark matter, 70% dark energy, which is very fun because I say I'm a cosmologist, I study the universe. We understand about 5% of the universe if we're lucky. Dark matter, dark energy, we don't really know what they are, and that's 95% of the universe. So I guess, we should figure things out. That's kind of our job. So I'm seeing a lot of people asking if I'm going to talk about the grand unified theory. Isn't the theory of everything above grand unified theory, and has grand unified theory been solved? We were guaranteed the grand unified theory in this live. Not today. I don't think I promised anyone that we're going to solve the biggest open question in physics today on this live stream. Just to give you some ideas here about what people are talking about with grand unified theory and theory of everything. So there are 4 forces in the universe. I will get to the Daisy question and the new physics question in a minute. There are 4 forces that control the universe as far as we know. Everything that interacts via one of these 4 forces. These 4 forces, there's them we're used to, like electromagnetism, electricity and magnetism. These are ones we're very, very used to. You know, I turn on a light switch, I have magnets on the fridge. We have those ones. Secondly, we have gravity. Gravity, we think we know gravity, right? I drop pen falls down. We stay in orbit around the sun, gravity. Then we have the strong nuclear force, which is responsible for gluing things together on the atomic scale, and the weak nuclear force, which is responsible for radioactive decay. And don't ask me more questions about the weak force. Out of these 4 forces, there is one we don't understand, and it is not the weak force, despite the fact that I always give a hand-wavy particle decay thing to it. The force we don't understand is actually gravity. The reason we don't really understand gravity is because it doesn't behave similarly to the other forces. When we talk about weak nuclear force, strong nuclear force, electromagnetic force, we are talking about how particles interact. When we talk about gravity, we are talking about how massive bodies interact. And it is very difficult for us to understand how gravity behaves on the particle level, on the quantum level. To understand this, we would need a theory of quantum gravity. Now, we know that in the early universe, some of these forces were united before the CMB was formed. Back at that time, the electromagnetic and the weak nuclear force were united in what is known as the electroweak force. There is then the question of if we go to even higher energies or earlier on in the universe, because in the early universe it was more energetic. This energy has kind of been diluted throughout the universe as it expanded. So the universe today is much less energetic than it was. But if we go back in time, if we turn up the energy, the temperature of the universe, electromagnetic and weak forces unite. So then there's the question of, previously, was the strong nuclear force also united? This would give us a grand unified theory, the unification of electroweak and strong nuclear force. This would give us the grand unified theory. And if you go even further back in time or higher energies, the question is, was gravity also united? Were they one force instead of 4 separate ones? And if you throw gravity into the mix, that is the theory of everything. So electroweak theory, we understand, we know how electromagnetic force and weak force were united. In broad terms, there's a lot we don't yet understand, but we understand that they were united. If you want to unify if you want to unify the strong force to the mix, you need a grand unified theory. If you want to also unify gravity, you need a theory of everything. Now, the grand unified theory and the theory of everything have not been solved. To my knowledge, they have not been solved in the last 4 months since my last live stream. I'm pretty sure I would have heard about this, read about this, or had some talks about this if that were the case. There are many different ideas, there are many different models of trying to solve these, but we do not yet have a grand unified theory. We do not have a theory of everything. I know there were several people here saying we were guaranteed the grand unified theory in this life. I do not believe I have ever promised that, but if at some point we do find the grand unified theory or the theory of everything, you can guarantee that I will do a live stream about it, assuming Cup of Cosmology is still up and running at the time. I will do a live stream about it because that would be a major breakthrough in physics. So, no, we are not solving grand unified theory, one of the biggest open questions in today's live stream. You know, that's not an 8 p.m. on a Sunday afternoon task. But if we ever do get that answer, you will hear about it here first. I mean, you'll probably hear about it on every popular science news page first, but you'll also hear about it more reliably here on Cup of Cosmology. Okay, going to answer Scott's question about dark matter, and then I'm going to go back to the question about Daisy and about dark energy, which was not directly the question, but that's how we're going to answer it. And then I still have Andrew's question about what is new in physics, which is related. That's the order of questions that I'm answering. Okay, I said the lambda CDM, our standard model of cosmology. We have lambda for the dark energy component, and we have CDM which means the cold dark matter component. So Scott asked a very good question of how cold is dark matter, like absolute zero kind of cold. Not that cold. As to how cold, we don't know exactly. Now, when we talk about particles or species being cold in the universe, what we actually mean is they move slowly. So we know that the more energetic something is, the faster it can travel. This is why we have things like neutrinos, which are a type of particle that travel really, really fast, almost at the speed of light. These are ones that have a very low mass. Now, when we talk about dark matter being cold, what we are saying is it travels slowly throughout the universe. It is kind of slow. And cold, the slower it is, the less likely it is to impact things like the formation of structures in the universe. If it's zipping about, then it's harder for galaxies to form on top of it. If dark matter is kind of trudging along slowly, it is easier for stuff to gravitationally pile on top of it. So when we talk about dark matter being cold, we're basically saying it can't move too quickly. It can't be too energetic. It's kind of cold. So then it has a lower energy. Now, as to the exact temperature, this is something we cannot exactly answer because we don't know. It depends on your model of dark matter. Now, we have different ideas where we say dark matter is like 1 GeV. I know that is not a temperature, but we always express it in terms of energy, even though we're talking about the mass or the temperature. So when we say dark matter is cold, we're saying, it could be 1 GeV, it could be TeV, it could be MeV. These are all electron volts, like tera electron volts, giga electron volts, mega electron volts. This is what we're talking about here. So it's a good question, Scott. I can't give you a specific answer as to how cold dark matter is. We just know it's cold. And we know it's cold because if it was warmer, galaxies would look different. So we call it cold dark matter just to distinguish it from hot dark matter or warm dark matter. So we know it's cold. How cold exactly? Somewhere between 0 degrees and some degrees. That's as precise as we can be, I'm afraid. Okay, back to the question about the dark energy spectroscopic instrument. So the question was, is there anything new from the dark energy spectroscopic instrument? Now, DESI, dark energy spectroscopic instrument, is a very, very cool ground-based telescope that is in Chile. Yeah, wow, how specific, between 0 and something. I know, right? That's as specific as I can be about dark matter, I'm afraid. It's cold. The thing is, I'm being vague because if you look at the whole available models of dark matter, you cover 80 orders of magnitude in mass. We rule some of them out based on different observations, but this is why it's very hard to know what dark matter is. We can't see it. You can't exactly put it on a scale and weigh it when you can't see it. So, there are models of dark matter where dark matter are clumps of stuff the size of stars. They're big. There are models of dark matter where your dark matter is a tiny particle zipping around. We don't know the mass of dark matter, and therefore we don't know the temperature of dark matter other than cold. It's chilly. That's it. That's all we can say about it. Okay. Dark energy spectroscopic instrument is ground-based telescope in Chile. In Chile? Yes. That is measuring galaxies and the distribution of galaxies in the sky. So what it is doing is taking the most detailed map possible of where galaxies lie in the night sky. I'm going to show you what DESI looks like. Let me just bring up my slides. And of course, it's going to start on the CMB again, just because that's my default slide to start on. I used to be able to pre-select the slide before showing it on screen. I can no longer do that. This is not the image I want. Now we have to go through until I find the image I want, which should be the next one, I believe. Bear with me. Here we go. Okay, so what DESI is doing is taking this very, very incredibly detailed map of the night sky. Now, what you can see here is the map that DESI released last year. Every dot on this image represents a galaxy. So if you look at the image in the background, you can see it's kind of shaped like that, where you have data up here and down here. This is basically our galaxy lies across the center. So we take images looking up and looking down, basically. So we have these two different parts of the sky that we look at. Zooming in here, you can see that every single dot here is a galaxy. There were already 6 million galaxies mapped when DESI released this map. It is the most detailed map we have of the galaxies in the night sky. Now, DISY released this map last year, and the cool thing is not just taking these pretty pictures. The reason it's doing this is to study dark energy. Now, the way we study dark energy with this is because if we assume that the universe has a lot of dark matter holds galaxies in place. It's the scaffolding of the universe. Dark energy, on the other hand, is pushing everything away from everything else. So dark energy is kind of making the distribution of matter change over the course of time. So what we can do with DISY is we get different slices each one going further and further back in time, because the further you look in the night sky, the further back in time you're looking, because it takes a while for light to reach us. Light has a specific speed at which it travels. So with the DISY instrument, you can take the close by galaxies that it's mapped and the far away galaxies that it's mapped, and you can see how their layout is, how they're distributed, what they look like. And this gives you an idea of how the distribution of matter is changing throughout cosmic evolution. This is something that allows us to study dark energy. How has dark energy behaved over the course of the history that we can observe with DISY? Now, DISY results came out last year, the first ones, and even 2 years ago now. I believe it's 2004, and then they doubled down on it at some point. No, it was 2005. It was 2025, not 2004. What are 20 years, plus minus 20 years. Yes, it came out in 2025, last year, yes. So the cool thing that DISY found is that dark energy doesn't appear to be as constant as we thought it was. So when I talked about dark energy, when I had the pie chart up, I said dark energy in the standard model is constant throughout cosmic evolution. It's a cosmological constant. DISY results found a small preference for time-varying dark energy. So time-varying dark energy means that dark energy is going to change its behavior throughout the universe. It is thawing, in a sense. So the way dark energy behaves today is not exactly the same as the way it behaved in the early universe. Now, the first DISY results that were released were not completely conclusive. It was just kind of, we find a mild preference for this model compared to the cosmological constant model. Then there was the second DISY release a few months ago. I believe I have already talked about this on my live streams. The second DISY release just kind of confirmed what the first one had found, reaffirmed that they do find a preference for time-varying dark energy. Now, this is something that we should check with other experiments that we have ongoing. So this was the status already a few months ago. DISY results are showing mild preference for time-varying dark energy. And this was found also in their second data release, so it doesn't appear to just be a statistical fluke in their first data release. Now, there has been no update from DISY in the last couple of months, beyond saying, data release 1, data release 2 kind of agree with each other. However, I can tie back to Angie's first question of what's new in physics. So what's happened in the last few months is we have different dark energy experiments that have released updated information. Now, I didn't have time to prepare slides on this because I was just did not have time to do that today. But so another experiment that we can talk about is the Dark Energy Survey. Confusing names, I know. We have DISY, Dark Energy Spectroscopic Instrument, which is ground-based, and then we have DES, the Dark Energy Survey, which is a space-based mission that is also trying to study dark energy. Now, the way this works, DES, the space-based one, the way this works is by looking at the shape of galaxies and seeing how galaxies are distorted and seeing how this changes when you look at different patches in the sky, again, to study how dark energy behaves. Now, this was running between, I believe, 2013 and 2019. It was a 6-year mission. Now, the thing about these space missions is it takes a very long time to clean all of the data, to release all of the data, to analyze all of the data. So usually the data releases are substantially behind the data collection. The clearest example we can think of this is the data we have for the CMB, my cosmic microwave background ball back here. The most precise mission we have for this, that we had for this space-based mission at least, was Planck. Planck ran between 2013 and sorry, between 2009 and 2013, and the last data release was in 2018. So it took 5 years to clean up all the data. The Dark Energy Survey took data between 2013 and 2019, so it was a 6-year mission. We had this year 1 release, we had this year 3 release, and finally, a few weeks ago, I believe in early December, this year 6 was released. So this year 6 is the final data release from the Dark Energy Survey. So it is the kind of the final thing we're going to hear from the Dark Energy Survey. It has been an incredible amount of work from a bunch of people, but we finally have the last data from this. Yeah, now we just need a dark energy projects called DE and D just to make it more confusing. Okay, so just got a cat walking across the screen. Again, at least the keyboard's off this time. Hello, cat. Do you want to come say hi? No, you get a cat tail, but that's all you're going to see of Otto. Just his tail. Yeah, you can jump up. You don't need to take the key. Okay, he will figure it out. He's trying to get to the cat tree, and apparently it's confusing today. So, what the Dark Energy Survey found in the last data release, they found that the way matter clusters is slightly different to how we expect within lambda CDM. This is something that we have seen in other experiments. This is something known as the clustering tension or the S8 tension, the sigma 8 tension, depending on your perspective. This has been consistently found by 2 missions, and it's kind of like a move away from what we'd expect in standard cosmology. There was a mission, another mission called KIDS, that last year found that actually maybe we don't have this tension anymore. I did a whole stream about this last year. I think it's just called KIDS Results. Did I do a whole stream about it? No, it was in my what's new in cosmology stream, which I did in kind of April-ish last year. Oh, cat's back. Apparently my laptop is a better bed than his cat tree. So results from this, there is still this clustering tension, even though the other experiment no longer finds it. But the very interesting thing from this is that they find that both lambda CDM, our standard model of cosmology, and time-varying dark energy fit the data equally well, which means we can't really tell them apart based on this results. So some people were hoping that this year 6 would either confirm the DISI results or disprove the DISI results, and instead the results from this are kind of inconclusive in that regard, basically saying we don't find a clear preference for either, which is already in of itself very interesting, because we're basically saying that, hey Baz, good to see you again. It's been a while since I've seen you in the streams. So what we're basically saying is the data is equally well described by standard model of cosmology and by time-varying dark energy. So this is very interesting, because if the DIS result had been clear-cut of yes, we find standard lambda CDM, standard cosmology, then it would be, then we would say okay, the DISI results are inconsistent. But because the DIS results are kind of in between, it's still compatible with all other missions. So it didn't solve any problems, but it's also interesting as to why DIS didn't find standard cosmology either. So this is something that happened very recently, a couple of weeks ago, and it's very interesting. Now, question to all of you. A few years ago, I believe in 2021, back when these streams were still on Periscope, it was even before the HAPS days, I believe, I did a whole live stream about the DIS results back when we had the first DIS release, and I had someone from the DS mission join on the live stream and talk about the results. That stream, I'm not even sure if it's on YouTube. It was back in the Periscope days. So question, do you all want me to get someone from DS to come and present the new results on the live stream? If so, it might be a repeat guest. We'll see if this person is available. But if people are interested, I could do a whole stream about this and the year 6 results and what they tell us. This is something that obviously I can prepare for today, but given that the results have just been the final release has just happened, we could potentially do a stream about that. I could potentially get someone from DIS to join us. Okay, so that's one cool thing that has happened in cosmology since the last live stream, because the last live stream was 4 months ago. These results were released a few weeks ago. If I'd had the forethought to prepare for the stream longer than a few hours in advance, I would have shown you the images and the results, but I didn't do that. So instead, you just hear me telling you that these results are cool. Guest, please. Yes. Okay, so let me just pause here before I jump into what else is new in cosmology. It's been quite a while since I had a guest on Cup of Cosmology. The reason for this is because my streams became very kind of erratically scheduled, it became harder to fit in guests. I'm aware that it's been a long time since I had guests on the stream. I do apologize for that. That said, I have some people in mind and some topics in mind. I unfortunately did not write any of this down, so I'm just kind of remembering what I had planned several months ago. But I believe there was a request for a stream on neutron stars. So I will get an expert in Helsinki working on neutron stars, not yet sure who, but I will find someone in Helsinki working on neutron stars to come on the live stream. We also might get at some point soon-ish a stream about space clouds and how space clouds are formed, and potentially a DIS stream if these are the ones that people are interested in. I believe there was some other one at some point about quantum entanglement that we thought we might come back to, and potentially I've been asked several times based on the questions that are jotted down somewhere on this piece of paper. Apparently, at some point, someone asked me the definition of mass, and I believe my response was, I'll get a quantum field theory person to come and tell you what that is. So I have ideas for live streams. And as always, if there is a specific topic that you want to hear about on the stream, either by me or by a guest, there is a way you can request topics on Cup of Cosmology. The way is to go to cupofcosmology.com, and there's a section there of request topic with instructions, but the instructions are basically message me, we agree on a topic, and then you do a donation of a specific amount to one of the charities that I sponsor on Cup of Cosmology, and then I will do a whole stream or half a stream about the topic of your choosing, and that may require getting an expert involved. So if you have a very niche topic, like if you want a 1 hour long stream about blue dwarfs, there is a way you can request that. Now, usually these streams are just me rambling or me talking about a specific topic with or without guests. But you can request a whole 1 hour stream or a 60, 90-minute stream about a topic. Instructions are on cupofcosmology.com. This has happened a couple times. If you want to request a topic, please go ahead. But yes, I have some potential guests in mind. I will see what we can do about this, see if we can get someone about this to join as well. And there's a bunch of people at work who have said they want to join at some point. I just need to set that up. Tea is now perfect temperature, 33 minutes into the stream. Friend of mine was laughing at me the other day because I made tea and ignored it for 30 minutes, and my friend was worried that my tea was getting cold. I'm like, no, it's getting perfectly drinkable. As we have checked many times in these live streams, the tea is perfectly drinkable when we're approaching the 35-minute mark. Oh, you want someone to explain superposition so you can both understand it and not understand it? Yeah, we can do that. I have cats. I can get a box. We can do Schrodinger's experiment. I mean, not really, because I'm not actually going to risk my cats, but I can put the cats in a box and explain the Schrodinger's cat experiment. But obviously, no cats will be harmed in the making of this experiment. See, I say that, and he's just walked off of the laptop and gone away because I clearly upset him by mentioning putting him in a box. As every cat owner knows, there's a big difference between putting a cat in a box and letting a cat jump in a box. Okay, question from James. I still want to come back to what else is new in physics, because there's one other thing I wanted to talk about. What was the other thing I wanted to talk about? Yes, there's one other thing I wanted to talk about. But before I get back to that, yeah, just make the tea half an hour before I start. No, that's not how it works. No, Scott, that's wrong. The tea is made as the last part of my preparation for the live stream. I get my freshly made cup of tea, I come and sit down and I start the live stream. I can't make the tea half an hour beforehand. That makes no sense. Also, then I'd start the stream and immediately be drinking. But now we get to have a midstream pause while I drink my tea. Okay, question from James. This info haunted me for 4 months. Oh no, what did I say last time that has haunted you for 4 months? Probably related to the question, what is mass? Does gravity's effect travel as a wave? If the sun disappears, would the gravitational loss only be felt after 8 minutes? Yes, not a dumb question. This is a very cool question. Yes, gravity does travel as a wave. And this is something that we got proof of in 2016. So we know that the electromagnetic force also travels as a wave. There is the light wave, there are magnetic waves, magnetic fields, there are light waves. Gravity also travels as a wave, and this is known as gravitational waves. And gravitational waves are just one of the most amazing things in the universe. I'm so glad you asked this question, James. I get to go on a tangent about gravitational waves, and then I'll come back to, supermassive black holes. Who cares about that? We can talk about gravitational waves first. Supermassive black holes is the other new thing in physics I want to talk about. We'll get to that. Gravitational waves, we go. Yes, so gravity does travel as a wave. This is known as a gravitational wave. So a gravitational wave is basically just a ripple in the fabric of the universe. It's a ripple of space and time. If a gravitational wave were traveling through you, like from me to you would feel it by first getting taller and thinner and then shorter and fatter. This is the effect that a gravitational wave has on kind of a ring of particles, if you want. Now, this effect is insanely small. Imagine two black holes smashed together produce a huge amount of gravitational waves. They pass through you here on Earth. You would get taller by a billionth the width of a human hair. It is a tiny, insignificant difference. It is a difference, but it is a tiny, insignificant difference. And these gravitational waves basically carry gravity. So they are a gravitational distortion. Now, anything in the universe that is moving in an erratic way, in a non-symmetric way, can produce gravitational waves. For an example, if I'm here on my chair and I rotate at a constant speed, I do not produce gravitational waves. However, because it is symmetric. However, if I am rotating here and flapping my arms about wildly, it is no longer symmetric. I am now producing gravitational waves. I am causing these tiny ripples in the universe. Anything moving through the universe can produce gravitational waves. So, for an example, black holes smashing together produces gravitational waves. Supermassive black holes smashing together, gravitational waves. Small black holes falling into big black holes. Supernova exploding. All of these produce gravitational waves. And anything with gravity is going to distort the gravitational field as a kind of wave effect. So, hypothetically speaking, in your question, we have the sun. We just make the sun disappear. Let's not question how. We just make the sun disappear. How long would it take us to know? It would take us 8.5 minutes to know, because the sun is about 8.5 light minutes away from Earth. It takes 8.5 minutes for the light from the sun to reach us. It also takes 8.5 minutes for the gravitational effect of the sun to reach us. So if you just pluck out the sun, we would not immediately be shot out of orbit. We would have 8.5 minutes before everything would go dark and we would gradually drift away from our orbit. Now, this is another cool thing. Now, there is no inherent reason why gravitational waves travel at the same speed as light waves. This is something that Einstein predicted. Einstein's general relativity predicted this, but it doesn't have to be the case. There are a lot of modified theories of gravity where gravitational waves travel at different speeds. Now, a couple years ago, 2016 to be precise, we got the first direct evidence ever of gravitational waves. The LIGO experiment, Laser Interferometer Gravitational Wave Observatory, here in the US, here on Earth in the US, actually measured gravitational waves directly, gravitational waves coming from two black holes spiraling around each other and gradually merging and colliding. We found these gravitational waves. Since then, we found about 120 more gravitational waves coming from merging black holes. We have also found gravitational waves coming from merging neutron stars. Neutron stars are just a specific type of star that is really, really dense, but not quite dense enough to be a black hole. But it's kind of a star that is dense enough to fuse things together so you get neutrons, a star made entirely of neutrons. So, neutron stars, when they crash together, will produce a huge amount of gravitational waves, but they will also produce gravitational waves, and they will produce a flash of light. So when neutron stars smash together, this is something we can measure both with gravitational waves and with electromagnetic waves. We can measure it with gravitational wave detectors and with gamma ray detectors and radio wave detectors. And this is what happened in 2017. We got the first measurement of two neutron stars smashing together, measured both in gravity and in light. Based on the arrival time of these signals, we were able to see that, yes, these travel at the same speed. So we were able to confirm that gravitational waves do in fact travel at the speed of light. And this is very, very cool because it means that if you like Einstein's gravity, this is cool. If you like modified gravity, this was kind of a bad day because it ruled out a lot of modified gravity theories on the spot. So it is not so much the cosmic speed limit, like it is the speed limit, it is the upper limit, but there was no reason why gravity could have traveled slower, for an example. But based on these neutron stars smashing together, we now know that gravitational waves travel at the speed of light. And just to clarify here that there is a slight difference of gravitational waves and gravity. Like gravitational waves carry gravity. And I mentioned that anything non-symmetric produces gravitational waves, but a massive object will still produce gravity even if it's perfectly symmetric. Anything with mass distorts the gravitational field. Anything that is moving through the universe, in addition to having its own gravitational field mass, will induce these ripples. Now, we don't currently get ripples just from the sun. This is not completely true, but just if we consider the sun by itself, that does not produce gravitational waves. It does produce gravity. But if you suddenly pluck the sun out, that is going to have a ripple effect. It's kind of like the gravitational. Imagine the sun is here, it's warping space time. You pull out the sun, this is going to go back up. That is going to produce gravitational waves. And that is something that would take us 8.5 minutes to find. So even though the sun is a perfect symmetrical frozen circle, not completely, but we can model it as such, it does still exert gravity. It does still distort space-time by creating a big kind of well in the fabric of space-time. But it doesn't produce gravitational waves by itself. However, if you remove it, it will take 8.5 minutes for this effect to reach us because we know that gravity travels at the same speed as light, which is very cool. And yes, sun disappears, takes 8.5 minutes for us to realize that. Comment from Angie, you remember the stream I did right after the announcement? Yeah, I still have this stream. So usually my live streams are like planned here at home. Right after the announcement of LIGO having found gravitational waves, I popped outside of my institute and did a live stream. I think I was speaking at about 300 words per minute, and it was basically me just being like, gravitational waves, so cool, so cool. The amazing thing is now I actually work on gravitational waves. I used to work on the CMB, my favorite thing over here. Now I actually work on gravitational waves, which is really, really cool. On the topic of gravitational waves, I want to talk about how we detect them because I will never get over how cool it is, the method we use to detect gravitational waves. Why am I being glared at by two cats? Okay, so I will never get over how cool it is, like the way we've come up to measure gravitational waves. So I mentioned that if a gravitational wave goes through you, you grow by a billionth the width of a human hair. This is a ridiculously small amount. It is ridiculously difficult to measure this. In fact, when Einstein predicted gravitational waves in his theory of general relativity, he made the comment of, we will never have the technology to measure these, which of course is wrong. We did measure these. We proved him wrong, we proved him right and proved him wrong. But the way we measure these is by using lasers. So one thing we know about the universe, one of the things we know, is that light will always travel at the same speed. And this might seem counterintuitive when you start thinking about it. We're accustomed to speeds being kind of relatable. If I'm running on a platform and a train goes by, I will measure that train traveling slightly different to someone or slightly slower to someone who is standing still on the platform, because my velocity and the train's velocity are kind of added together. If I'm running and I throw a ball, that ball starts with a bit more velocity than if I'm stationary, standing still, throwing a ball. We expect velocities to be added together. That is not true for light. You can shine a light beam while standing here. Still, you can shine a light beam while running almost at the speed of light, hypothetically. The light will still travel away from you at the same speed of light. It doesn't matter what you do. It doesn't matter how fast you are traveling when you emit this beam. Light will always, always travel at the same speed, which means we can use it to measure things. Now, the problem with gravitational waves, apart from the fact that they're ridiculously small, is they distort all of space-time. So imagine I have this pen and I say this pen is 15 centimeters, 6 inches. Yeah, let's go with that. This pen is 6 inches. No one's going to call me out on that anyway, right? We all know what 6 inches looks like. 6 inches, 15 centimeters. Now, the problem is, if a gravitational wave goes through this pen is also going to get bigger or smaller. So it's no longer 6 inches. It's no longer 15 centimeters. It changes. So the question is, how do we actually measure something if all of our measuring devices change? But the thing that never changes is the speed of light. So what we do to measure gravitational waves is we construct two arms, a detector with two arms. Each one of these arms several kilometers long. For an example, LIGO, these are 4 kilometers long. And you send the laser back and forth down these arms. This laser will bounce off of a mirror and come back. And what you do is you set it up so that when the light beam comes back, it cancels each other out. So you have light moving one way, light moving another, it cancels each other out. However, during this time, if a gravitational wave passes through your detector, your arms are going to get taller, longer or shorter, depending on the gravitational wave, which means the light on each arm is going to take a different amount of time to return. It's still traveling at the same speed, but it has to travel a different distance. We know that velocity or speed is just distance over time. If the velocity is constant, the speed is constant, and the distance changes, the time has to change as well. So the time of arrival of these lasers changes, and then we no longer get the right pattern in our detector. And based on that, we can say a gravitational wave went through our system. So this is really cool. We decided, how do we measure these tiny, tiny differences in distance? Turn light into a measuring device and shoot lasers back and forth down these tunnels to see if the length of the tunnel changes at all. Hey, Chris, great to see you. I haven't seen you here in a long time. Chris was a one-time guest on Cup of Cosmology talking about interdisciplinary science. It was a very cool live stream. That one should absolutely be up on YouTube. So, gravitational waves, we use lasers to measure gravitational waves, which is so, so, so cool. Yeah, don't quote me on this being 6 inches. I'm just absolutely doing this by eye. This looks like it's probably about 6 inches. Don't feel bad if that doesn't seem like 6 inches to you. So, yes, as always, you'll know you come for the science, you stay for the definitely perfectly innocent comments and jokes that I make. So, gravitational waves are measured using lasers, which is really, really cool. We have machines here on Earth, we have detectors here on Earth measuring these gravitational waves. We have LIGO, we have Virgo, we have Kagra. These are already taking data and already measuring gravitational waves coming from black holes smashing together, neutron stars smashing together. It's amazing. It's amazing that 100 years ago, people were like, no, we'll never be able to measure these. And now you can literally download an app and get notifications anytime LIGO measures something. And you just get a pop-up like, gravitational waves from black holes found, and you're like, cool story. Yeah. Right? It's amazing that we're now at the stage where you can just be like, oh, look, we have more gravitational waves. It's an app now. It's not even something, we can just get an app notification. It's amazing. We don't need an app for everything, but we do need an app for this because it's just cool. Okay. But even cooler than using lasers here on Earth to measure gravitational waves is, what if we do this in space? What if we send the gravitational wave detector to space to measure smaller gravitational waves? And this is exactly what we are planning on doing. There is an upcoming space mission called LISA, the Laser Interferometer Space Antenna, which is going to be 3 satellites in a triangle chasing behind the Earth as it orbits the sun, about 7 degrees behind the Earth. These 3 satellites are going to send lasers back and forth between them in a very cool way of keeping masses in perfect position, laser shooting back and forth. And it's going to do this to measure gravitational waves going through the detectors. LISA is going to launch in 2035, 36-ish. I feel like I change that number every time I mention it. It's always 10 years away. It's like the town that is 30 kilometers away. It's a very niche inside joke there. But LISA is always 10 years away, 2036. Last year we were saying 2035. Now I'm saying 2036, 10 years from now. So we're going to send these 3 satellites to chase around the Earth, looking for gravitational waves. And this will measure gravitational waves coming from supermassive black holes smashing together, small black holes falling into big black holes. A lot of astrophysics, a lot of things like white dwarfs in our galaxy merging around each other, and potentially the ones that I'm working on and the ones that I'm interested in, gravitational waves coming from the very, very, very early universe. Now, if I say that anything that is non-symmetric or moving in a dramatic way in the universe is producing gravitational waves, what happens when the universe was experiencing these dramatic changes like, inflation, where the universe grew dramatically? Or I mentioned before about the forces and we had the electroweak the electromagnetic and the weak forces at some point broke apart, that's got to be a dramatic effect, right? A lot of these effects could produce gravitational waves, and these would basically just be a background of gravitational waves in every direction you look in the universe. And LISA, the upcoming space mission, might actually be able to measure these gravitational waves coming from tiny, tiny, tiny things that happened in the very early universe, which is so cool when you think about it. So just to recap, we are sending satellites to chase after the Earth, shooting lasers back and forth, and we're going to try to use that to figure out what happened 14 billion years ago in the universe. It's amazing. This is what I work on. So we have this map. We have my CMB, cosmic microwave background. This is the oldest light we can see in the universe in any direction we look. This was 380,000 years after the end of inflation. What would a map taken 3 seconds after the end of inflation look like, or less than a second after the end of inflation, the first second of the universe? Imagine if instead of a map of light, we could do the same with gravitational waves coming from the early universe. This is not just a fantasy, this is something we might have in 10, 20 years. And that's what I'm working on now, which is, again, so cool. It's so cool that we get to do this. So thank you for the question, James, about gravity, because it allowed me to go on this tangent about gravitational waves. Also, I appreciate the question because it's one of the prompts that I put in the YouTube description. I always put random questions in the YouTube box at the bottom, like in the video description. And they're prompts, they're like, if no one else knows what to ask, I will address those questions. And today, I think the first one is what's new in cosmology, which is the question Ange asked, and I've only partially answered. And the second one, or the third one, is what are gravitational waves, and I think the other one is what is dark matter, which I've also already answered. Coming back to gravity, because I see there's a couple of questions here where maybe I wasn't clear about what I'm saying. Question from James. Are we saying that all objects have gravity, but not necessarily gravitational waves? Yes, basically. So as Scott is saying, the direct follow-up here, observable gravitational waves only propagate when massive objects interact in asymmetrical ways. Yes. So if you imagine space-time to be a sheet, any object with mass is going to distort the sheet. It's going to kind of pull it down. It's like a trampoline. Let's go with a trampoline. If you put an object on a trampoline, it's going to kind of bend around that object. Space-time is going to bend around any object with gravity, with mass. And this is what we interpret as being gravity. But gravity itself takes a while to travel, and it travels via gravitational waves. You can imagine when, like, here's your trampoline. I put the sun here in the middle. It's going to distort space-time. This distortion is going to ripple out, and it would take kind of 8.5 minutes before people on the Earth realize that the sun has just appeared. Obviously, this is not how it happens, but just if you put a sun there, that's how long it would take us to feel it. So the act of putting the sun there would produce gravitational waves. Removing the sun would produce gravitational waves. While the sun is just there, the amount of gravitational distortion is not changing. So a gravitational wave is kind of a change in the amount of gravity. It's not just carrying gravity, it's carrying the changes in gravity. So while the sun is sat there doing its thing, it is not considered in isolation. There's a caveat that I'm going to come to. Considered in isolation, the sun is not producing gravitational waves currently. But if the sun started moving, then it would ripple out and take 8.5 minutes to reach us, because the effect of gravity will travel via gravitation, or the changing of gravity will travel as a gravitational wave, and that is something that we will then feel 8.5 minutes later. So any object with mass in the universe produces a gravitational disturbance. Anything that is changing this gravitational disturbance, or a change in the gravitational effect, travels as a gravitational wave, and this travels at a finite speed. So yes, we will always have a gravitational presence, but not necessarily gravitational waves unless there's a change in the gravitational presence. Now, I keep saying caveat applies to this whole thing because technically, anytime you have two bodies orbiting around each other, you are going to produce gravitational waves. Now, even though we always think the sun is here, the Earth is orbiting around it, there is a small kind of effect that the Earth has on the sun. Now, it's very, very small because the Earth is very small compared to the sun. But as the Earth orbits around, the sun wobbles very slightly. It also wobbles very slightly because of Jupiter, which is much more massive, but all the planets cause a slight wobbling of the sun. Very, very, very tiny. But that means that if we consider the Earth and the Sun system, there is this tiny back and forth reaction, which means the sun is moving very, 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 very slightly due to the Earth's presence, which means that the Sun-Earth system do actually produce gravitational waves. So the sun itself does not produce gravitational waves, but the fact that the sun wobbles slightly due to the Earth and Jupiter and all the other planets, that does actually produce a small amount of gravitational waves. Similarly, the Earth and the moon is also having a small effect on the Earth. So the Earth-Moon system will produce a tiny, insignificant amount of gravitational waves. But if you just look at the moon by itself, you wouldn't say that is producing gravitational waves. But the system of the two objects will produce gravitational waves. If that makes sense. If not, do ask again. And James, again, you are not asking bad questions. These are all excellent questions to ask. As always, there are no bad questions here. There are just questions waiting to be answered. Please do feel free to ask anything. There is no such thing as a bad question. There's no question I won't enjoy answering. I can guarantee you will never ask something that I'll be like, oh, I don't want to answer that. And if that's the case, I just won't answer it. But these are not bad questions. These are all excellent questions. And by now, my tea is definitely cold. That was like an hour since I made this tea. Okay, we have a really excellent question here from Prath. Sticking to the topic of gravitational waves, and I got hyped about Lisa and early universe gravitational waves. Excellent question from Prath here of how can you be sure that the gravitational wave detected is indeed from the early universe or just a small collision that is too sensitive for LIGO? Excellent, excellent question. Love that question. Answer one is this is exactly what I'm working on. But the important thing here is to distinguish between an event that is happening once and a continuous event. Now, when we think about two black holes smashing together, this is an event that happens and then stops happening, right? We have the two black holes, they are gradually going to spiral around each other, merge, collide. They stop producing gravitational waves once they've collided. So this is something that happens for a short amount of time. The ones we've seen at LIGO, for an example, the signal lasts like a few seconds to a minute, something like that, but it is short. However, the gravitational waves that would have been produced in the early universe, it's a finished process, but the gravitational waves would still be everywhere in the background of the universe, much like the cosmic microwave background radiation. So it would not be a short-lived event. It would be something that we would measure continuously over all 4 years that LISA is taking data. For the 4 years of LISA data collection, you would have this background. This is actually very similar to what's happening. I'm going to use this again as an example. So just want to compare. I'm going to bring up the CMB map again. Bear with me as I find my slide, because I want to compare the two different versions that I have, because you'll notice they're not exactly the same. And then I can tell you why. Let me just go back to the CMB map. Here it is. Thinking about it. So you see, the one that I'm showing on the screen is just the blues and the oranges of the cosmic microwave background radiation, the background light. The one I'm showing here has this red bar in the center. Right? As you look around it, there's this red bar in the center. Now, these come from different satellites, but the difference is the one that you see on the screen has been more cleaned than the one you see here. And what I mean by that, let me just go back to me here. What I mean by that is the one that you normally see on my screen has this red bar removed. So what this red bar is actually the galaxy. This is our galaxy that lies at the center that is producing a lot of bright light. So it's kind of blocking the background light, right? But we can pull it apart because we know that this is the galaxy and everything else is the background light. So you can separate these two. Now, what you might get when you're looking for gravitational waves is some things that happen for a few seconds, for a few minutes, for a few days. And then ideally behind everything else, you will have this background hum of gravitational waves. So in the same way that we can pull the galaxy out of the CMB because we know that it's there, if you measure something that only happens for a few minutes, and what you're looking for is the hum behind everything else, you can remove these extra ones. This is very difficult to do, but this is what we're working on. This is why the work already starts now, is figuring out how precise do we need to have our data? How precise do we need to have the tools and the techniques? How can we actually remove these small signals, these what we call transient signals, which they happen and they stop happening, from the ones that are happening continuously. Now, to add, won't the momentary gravitational waves merge into the background and pollute the signal? Yes, but they happen at they have slightly different shapes. They have slightly different kind of signals. The signal to noise would change. The signal to noise ratio would change. So you always have this background hum, and then say like once a day you get something on top of this background hum. So these things that go on top, kind of like you have, this is your baseline gravitational wave signal from the early universe, assuming it's there, caveats apply, then you might have something jump on top of it. And that is what you hope to remove. The bigger problem comes from other things that can produce what we call a background signal. The clearest example of this is white dwarfs in our galaxy. So our galaxy is full of white dwarfs. White dwarfs are very dense stars that are not yet a neutron star, not yet a black hole, but still very big. There's a couple million, like 10 million white dwarf pairs in the galaxy. And the white dwarf pair is going to be spiraling around each other extremely slowly. It's not like a black hole where it's done. These white dwarfs are going to take a very long time to do this. Like black holes do as well. The bit we detect is the final dance. White holes merging around each other can take a long time because they're slightly less massive than black holes, so they take the time about it. With 10 million white dwarfs in our galaxy, constantly merging around each other, slowly getting closer and closer, this is a lot of gravitational waves. And these will actually also produce a background of gravitational waves. So a lot of the work we are doing, specifically here in Helsinki, this is what I've got 2 papers on, is what I've got another couple of papers coming out on, is asking the question of how can you separate the background of gravitational waves coming from white dwarfs from a potential background of gravitational waves coming from the early universe? How can you tell these apart? That is a question we have 10 years to figure that out, right? Is how we will tell them apart. There's different tricks you can do. You can use the fact that, for an example, one thing that we did in a paper of mine, and that other people have also looked at, I'm not saying we're the only ones who have done this, is the fact that as Lisa is going to be chasing the Earth, and the Earth moves around the sun, and the sun is, in one of the galaxy arms on a different plane, at different points of the year, we're either staring more directly into the galaxy or away from the center of the galaxy. If we are at the point of the year where we're staring closer to the center of the galaxy, we are going to see more white dwarf binois. At the time of the year where we're staring away from the galaxy, slightly more away from the galaxy, we are going to see fewer of these. So this means that the galactic binary is going to have a kind of annual modulation. It's going to have a pattern. If you take data for a year, what you will see is something like this. This is frequency, or like this is time 0, this is 1 year. This is the gravitational wave signal. So in here you have signal, this is your signal here inside. And throughout the year, you will have these kind of 2 bumps where we're staring to the center of the galaxy, away from the galaxy, center of the galaxy, away from the galaxy. So this here is not what you would see with a signal coming from the early universe. A signal coming from the early universe would instead be something like this, just everything inside here. So one thing you can try to do is look if your signal changes over the course of a year. If it does, it's less likely to be an early universe signal. This got very technical. This is basically a plot from my last paper, but obviously like a better version of it. This is obviously the better version. So we went on a very technical tangent here, but bringing it back, we have this future space mission, LISA, which is going to be 3 satellites chasing after the Earth, looking for ripples in the fabric of the cosmos caused by dramatic things like supermassive black holes merging together, or even things happening in the early universe. Finding these gravitational waves that happen in the early universe is extremely difficult because there's a lot of other signals sat on top. There are some signals we can remove because they're short-lived. We're hoping there are some we can remove because they change throughout the year. But finding this early universe gravitational wave signal is extremely difficult. It might not be possible. It might not even exist. And this is exactly what I'm working on, is trying to figure out how can we do this? How can we find this? What will Lisa be able to tell us about the early universe? And it's a very cool topic. But basically, we have space lasers, and we're using space lasers to try to figure out what the universe is made of. And that's kind of cool. But bringing it back to the question that James asked of does gravity take a while? Yes. So any massive object in the universe produces a gravitational effect. Any change in this gravitational effect is carried via gravitational waves. Gravitational waves travel at the speed of light. Because the sun is 8.5 light minutes away from us, if the sun stopped producing light, it would take us 8.5 minutes to see it. If the sun is sucked out and there's no longer a gravitational effect of the sun, it would also take us 8.5 minutes to feel it. So yes, changes in the gravitational field are carried with gravitational waves. We have actually measured gravitational waves. It's super cool. We're hoping to measure more gravitational waves again in the future. Very, very, very cool topic. So James, absolutely not stupid questions. So very, very good questions. I'm just going to do a quick read through because I was having fun on my tangent and I might have missed some questions about gravity and gravitational waves. Just going to recap here. Once I've recapped the gravitational wave ones, there is still one question I want to answer right from the beginning, which I've only partially answered and I want to fully answer. So we answered about does gravity's effect travel as a wave? We answered that one. We answered if the sun was symmetrical, would it still exert gravity? Yes, it does. Cosmic speed limit is the same, like the speed of light, speed of gravity, same thing. Yes, we answered these questions. Okay. I think we answered all of the questions about gravity and gravitational waves. Those were super good questions. I'm going to give you a sec to type up your final questions on gravity and gravitational waves. And then I'm going to go back to the question of what has happened in physics since the last live stream. I've already talked about the DIS results, which are not the same as DISY. But there's one other thing I wanted to talk about, which will only be brief because I read the article an hour before the stream. So cool. I agree, James. This is cool. This is such a fun topic. And the fact that we can draw parallels between the cosmic microwave background radiation and a potential background of gravitational waves is just so cool to me. And, I changed topic. I used to work on that. Now I work on gravitational waves. But they're both such cool topics. Yeah, if anything could ever drag me away from the CMB, it had to be gravitational waves. It's the only thing that could ever drag me away from cosmic microwave background had to be gravitational waves. Okay, so back at the beginning of the stream, there was the question of what's new in physics. And there's a lot new stuff happening gradually, but something that caught my attention, which I haven't thoroughly read yet, so this is going to be just kind of like piecing it together as we go. There is another open question in the universe. There's a lot of open questions in cosmology, but another one is, where do supermassive black holes come from? So we know that at the center of every galaxy, there is a supermassive black hole. These are black holes that are 1 million times the mass of the sun. Oh, Lisa, question before we jump into supermassive black holes. Question from Garth. Not sure if I've asked this before, but at Lisa scales, don't you have to account for the expansion of the universe? At those scales, the universe expands more than how much interference can be detected. No, we do not. Yes and no. So at the end of the day, a lot of what Lisa is going to be looking for is within our local neighborhood or our own galaxy. Now, when we talk about the expansion of the universe, this matters when you take a step back and you consider galactic clusters. Our close by neighborhood, we don't really need to account for expansion of the universe much. Now, you will get a slight delay in arrival time of your signal because the universe is expanding, but not substantially. And the LISA mission itself, that is, the arm length is 2.5 million kilometers. At that scale, you don't need to consider the expansion of the universe. The expansion of the universe becomes a bigger problem when you're doing things like DISY results or dark energy survey results, where you're looking at galaxies light years away. With LISA, we are kind of looking at things that are relatively close by. So the expansion of the universe doesn't become such a huge problem. Supermassive black holes we're looking for with LISA are in different galaxies, but they're also not like the other side of the universe. They're not billions of light years away. So while there is going to be some delay effect due to the expansion of the universe, it is not substantial enough to be a big concern in our experiments. I can tell it's been a while since I've done a stream because my voice is not used to me speaking for this long, which is also not true because I talk so much all the time anyway, but not like for an hour and a half by myself with no one to bounce things back and forth off of. There's another gravitational wave question up there on the wall of messages. Is there really? Did I miss that one? Oh, yes, I missed that one. Yes, I got to the momentary one and I missed that one. Okay. Yes, the one got lost there. If two objects orbiting each other cause gravitational waves that distort space less than one Planck length, do they actually make gravitational waves? No. If it's less than one Planck length, it's not in any way measurable. So a Planck length is the smallest distance that we can conceive of. If there's something producing a gravitational wave less than that, no, it doesn't exist because there's no length smaller than a Planck length. So if the effect is less than a Planck length, no, it's not a real effect. And that would have to be a very, very, very small gravitational wave. So no, if it's less than one Planck length, it doesn't exist. Planck length is the smallest size in the universe that we can in any way talk about meaningfully. But also, Planck lengths are a quantum thing. Gravitational waves are a gravity thing. Do you want to try to unite quantum physics and gravity in a live stream? Because if so, we're not doing it today. We get very close to a grand unified theory at that point, unless we have established that is not today's topic. Okay, I think that those were the gravitational wave questions that Barth had here. So, at the center of every galaxy, there is a supermassive black hole. These are black holes that are about 1,000,000 times the mass of the sun. These are massive, super massive. As the name implies, they are supermassive black holes. They are extremely big. Just to put this in context, the black holes that we've measured with LIGO merging together are about 30 times the mass of the sun each. We found local black holes that are like 100 times the mass of the sun. Supermassive black holes are about 1,000,000 times the mass of the sun, if not more. This is huge. This is impressive. But there is the big question of where do supermassive black holes come from? So there are different ways we can go about forming black holes, but the standard one, the one we commonly think about, is a star reaches the end of its lifetime. A star is a constant battle between gravity pulling things inwards and pressure pushing things outwards. As a star runs out of fuel to burn, the pressure effect is going to be less, and eventually the star will explode as a supernova, and what is left, depending how massive the star is, and what is left is going to collapse to form a black hole. So in the standard idea, black holes come from dead stars. A star dies, it produces a black hole. This means that black holes will be produced with approximately the same mass as the initial star had, a bit less because some of it is lost with the supernova. So how do we get black holes 1,000,000 times the mass of the sun, 1,000,000 times the mass of an average star? Now, of course, black holes will gradually grow. Black holes are big gravitational objects that will attract anything that is close by enough, and that will fall, and the black hole will grow. So black holes can grow. They can accrete matter, is the technical term. They can just eat other things up, and they can grow. But in order to go from a black hole the size of the sun or the mass of the sun to supermassive black holes, that's a factor 10 to the 6 difference. That's a factor 1,000,000 difference. In order to do that, you'd need to wait longer than the amount of times that stars have existed. Which means that your average star, the universe has not been around long enough for the average star to turn the average dead star to turn into a supermassive black hole. There's just not been enough time. Other ideas of how we have supermassive black holes are, what if these stars merged, and a bunch of these mergers happen every time you merge, the star gets bigger and bigger. But again, it just doesn't quite fit the picture of why does every galaxy have such a big supermassive black hole? Where do they come from? One other possible idea that people have looked at a lot is what is known as primordial black holes. Now, these would be black holes that skip the whole star stage, and they are just regions of the universe when the universe was in its infancy. You could have regions of the universe that were so dense that you could directly collapse to form a black hole. So space-time itself collapses to form these black holes. Therefore, you don't need to wait for stars to form. This is what is known as a primordial black hole, and they get a head start on normal stars because primordial black holes can already happen in the first few seconds of the universe, whereas normal stars would turn on in the first few million years after the end of inflation. So it gives us a couple million years head start. Is it enough? Depends on what you think about primordial black holes. Primordial black holes are hypothetical. We have not yet measured any. There are people who think that we have some evidence that might indicate maybe primordial black holes. It's an ongoing debate, but we don't have any clear direct evidence for primordial black holes. And even then, it's a question of would primordial black holes have had enough time to be big enough to be supermassive black holes that we see today? How would this happen? How? So this has been the status for many, many years of like, where do supermassive black holes come from? They're just there. We know they're there. Very technical answer, just baffled. Scientists baffled by the presence of supermassive black holes. So there was a new research paper that came out, I believe, in either late December or already in early January, recently, in between my last streams and today. So there was this new paper led by the ICG in Portsmouth. This is the Institute of Cosmology and Gravitation in Portsmouth, and the Center for Astrophysics in Harvard in the US. So one in the UK, one in the US. And they have used JWST, one of the most amazing telescopes that we have, taking kind of optical and infrared data. They have used that to measure the composition of kind of the abundance of elements in a specific galaxy. This is a galaxy that is quite old. It has the cool thing that this galaxy has a bit more nitrogen than expected. Now, all of the elements in the universe, apart from hydrogen and helium, are formed inside stars, which means all of the helium in the universe was formed inside a star. All of the oxygen in the universe at some point was inside a star. Nitrogen, carbon, all of the heavy elements, everything above, like lithium, was formed inside a star, which means, most of your body was formed inside a star. That's why we are all stardust. But this galaxy has more nitrogen than what we'd expect based on the amount of stars that are there. And what these scientists have found is evidence for primordial monster stars. This is the official name for them. This is not just me calling them monster stars. Primordial monster stars, which would be stars that are formed at the very first stages of galaxy evolution, because of turbulent flow. So a lot of gas moving around, gas being hydrogen and dark matter kind of moving around very quickly as these galaxies are starting to take shape. And these turbulent flows could be enough to collapse into a massive star, which they're calling monster stars because they would be about 1,000 to 10,000 times the size of a normal star. So they have found evidence for these monster stars. The short version is they have found evidence that this galaxy at least must have had monster stars about 1,000 to 10,000 times the mass of a normal star. Anything outside that region, the nitrogen amount is off. So there could have been these early universe primordial stars, which would have been massive enough and early enough to set the seeds for supermassive black holes. So the idea is you have this massive star that is formed because the universe galaxies are being kind of like turbulence, gas, boom, star. Very technical description, obviously. This is exactly how it works. So you form your massive star that is already 10,000 times the mass of a normal star. This star is going to be short-lived because it's so massive. It's going to burn, the biggest stars burn the fastest and the brightest, or whatever the saying is. It's not that, but you know what I mean. These stars would be so massive, they would not last long. So they would collapse to be black holes quite early on in the universe. So you have this turbulent galaxy forming. You form a monster star that is 10,000 times or 1,000 times the mass of a sun. That collapses to form a black hole. And there you have your early universe massive black hole that could set the seed for supermassive black holes. So we're not saying they have fully solved the mystery. What we're saying is these scientists have found evidence in one galaxy that there could have been these monster stars, and these monster stars could set the seeds for supermassive black holes, which is very, very cool. So I wanted to mention this because where do supermassive black holes come from has been an open question in physics for a very long time. And we might be a bit closer to solving that mystery. And I love the whole idea of you could have these stars in the very, very early galaxies. These stars form a couple million years before all the other stars form. They just, suddenly you have a massive star there that is short-lived and collapses to form a black hole. And we measure this by looking at how much nitrogen is around the galaxy. because you can't produce too much nitrogen in normal stars. You'd need supermassive stars to produce this amount of nitrogen. So basically, we might have got a step closer to solving the question of supermassive black holes, where the answer is maybe supermassive black holes come from supermassive stars that came from the universe being a bit messy in its infancy. So we now could have these very early universe monster stars that could have resulted in supermassive black holes. It's very cool. It's a very cool topic to think about. And I wanted to mention that paper because it appeared in a bunch of popular science places. You might have seen it advertised, like monster stars is catchy. And that is actually the technical term that is used also in the paper. So there's these monster stars, and people were hyped about, have we reinvented how supermassive black holes work? Not completely, but also not no. So that's kind of cool. So the question, and yes, at the beginning of the stream, what's new in physics since the last live stream 4 months ago? Two main things. There's a bunch of other things, but two that I wanted to highlight. The dark energy survey results, which show that time-varying dark energy and standard cosmology are equally compatible with the data. We cannot distinguish them. This means that we need more data from DISY in order to figure out what dark energy is. And then we have potentially taken a step forward toward understanding the origin of the supermassive black holes that live at the center of every single galaxy, which is also very, very cool. Question from Fasia. What if supermassive black hole galaxy formation is just star-planet formation on a much larger scale? Supermassive black hole formation. Yes, but the question is, how do you get to that much bigger scale, right? Look, how does that happen? Because if you look at planets, they are substantially smaller than stars. And if you want a planet to be, 1,000,000 times the mass of a star, how are you going to go about doing that? Because surely at that point, you can't have that much mass concentrated in one place in a galaxy. How would that work? Comment from Scotia. Kurzgesagt has a video on this that said it's theoretically possible that these stars could have had black holes inside them and still be a stable star on the outside. Yes. I think there was a Kurzgesagt that has come out since these results, actually. Yes, I have not yet watched it, but that is possible. Obviously, if you have such a big star, it could be that the core of the star has already collapsed to form a black hole. So you have a star with a black hole at the center. Very, very cool. Very cool idea. Also, if you don't follow Kurzgesagt, you should check out their YouTube channel. It is the second best science outreach channel after mine, of course. Let's ignore that they have like 17 million viewers. Obviously, I have to say that mine is best. Massive gas clouds whose center collapses to form supermassive black holes, and you're left with protogalactic disk. Potentially, yes. Or potentially inside the galaxy, you have these supermassive stars forming, and whichever one is at the center happens to end up being the supermassive black hole. The others will then collide and form into this supermassive black hole. So yeah, we could have these supermassive monster stars that set the seas for supermassive black holes, and this is very, very cool. So those are the two main new things I wanted to talk about. So thank you for the questions to help me get out to these two questions, to these two topics, because these were on my mind of these are things I want to talk about today. And the very first question of what's new in physics was perfect for me to answer these questions. And then the follow-up question of DISY results led really nicely into this. And we went on a tangent about gravitational waves, which allowed me to tie in the supermassive black holes, because these supermassive black holes, regardless of how they're formed, these supermassive black holes might be detectable with LISA when LISA launches in 10 years. Amazing. I love it. Love all of the questions, love all of the topics. Someone here with a very Finnish sounding name, new to the channel. Welcome. Great to have some new people here. Please do subscribe, stay, come back, join in anytime and ask any questions you want. It is great to have people here. Okay, almost at the 1.5 hour mark. This was a super fun stream. Thank you everyone for the questions. It's been really fun. I love all of the questions. I love the direction the stream took. And it was so nice to have all of you come back. I know it's been a 4-month break in Cup of Cosmology. There's always a risk when I take a longer break that people are just going to give up on the channel. I very much appreciate that you all came back. It's been 4 months. I understand that that's a long wait, but you all came back, and thank you for that. For anyone who came back, thank you. For anyone who's just discovering the channel, thank you. You're all welcome here. It is so nice to be back. It's just been super fun, and it's so nice to see all the regulars and have so many cool questions here. One more question here. Could you answer why can't we travel more than the speed of light? Yeah, so Basically, the speed of light is the upper limit of travel in the universe. It's the speed at which the universe talks to itself, or it's the speed at which information travels in the universe. And this is a number that you can pull out with the equations, and from what we've measured, we know that there is this limit. And we're just answering this very quickly because I'm wrapping up the stream here. So in order to travel faster than light, you need to accelerate beyond that speed. But there's kind of an inbuilt mechanism in the universe that as you get faster and faster, the amount of energy you need to put in just ends up with you losing mass instead of accelerating. It reaches a point where you can't put in enough energy to accelerate beyond the speed of light. It is a built-in limitation of space-time. And we know that gravity travels at the same speed, light travels at the same speed. You just can't accelerate beyond that speed because you'd need an infinite amount of energy to do so. And at some point you run out of energy. So you could say it's like the space-time mesh itself can't propagate faster than that, and that is true. Nothing in the universe can travel faster than light. It is the limit on which information or energy can be exchanged in the universe. And to try to go faster than that, you would need to have infinite energy, and you just don't do that. So it is an inbuilt limitation within the universe as far as we know. A very short answer because I'm wrapping up, but that was an excellent question. And if you want to ask more details on that question, tune in for the next live stream. Very quickly, comment from Scott. Could stars also collide? Yes. But they would not. Stars can absolutely collide if they're close enough. Any two objects in the universe that are close enough can collide. Gravity is starting to join light and time in my mind-blowing subjects. Yes. Gravity does join things together in amazing ways. It's very cool. We still don't know how to join gravity together with things. I highly doubt we'll be answering grand unified theory next live stream either. But you should tune in just in case we do. Okay, checking my calendar very quickly because I'm back today, but as we all know, my life is busy. But as soon as my calendar loads, I can confirm I do believe somehow, my next 3 Sundays are empty, which means there should be consistent Cup of Cosmology at least for 2 or 3 weeks, and then we'll see where we go from there. So Cup of Cosmology should be back next week, same time as always. That is 8 p.m. if you're in Finland, 7 p.m. if you're in mainland Europe, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. As always, there is a time zone converter on cupofcosmology.com so that you can figure out when the next stream is in your own time zone. Do check it out. Also, if you want to make sure you get notified for the next stream, please do subscribe to the channel, click the notification bell, and then you will get a notification about 30 minutes before I go live. As a general rule of thumb, you can always check the YouTube channel. I schedule the streams about 6 hours in advance at the latest. So if around 6 hours before I'm due to go live, there is not a live stream scheduled, then I'm not going to be live. But I always try to schedule it at least 6 hours in advance. But if all goes to plan, Cup of Cosmology should be back next week. And then we're going to try to get back into regular streams again. It really has been great to come back today. You know, whenever I take a break, I'm slightly nervous about coming back. Like, is everyone going to hate me for taking a break? Are people going to forget what Cup of Cosmology is? Am I going to forget what Cup of Cosmology is? But it went, so it's always nice to come back and be like, ah, yes, these are the people who just come here to hear me info dump about cool stuff in the universe. And it's so cool. So thank you, everyone, for being here. Thank you for all the questions, for all the comments. To everyone who's reached out to me in the last 4 months to check that I was okay, I also very much appreciate that. I did take a social media break, so I know I ignored a couple of you, but I did see your messages and very, very much appreciate you all checking in and just coming back today. So, Cup of Cosmology should be back next week, same time as always. I hope to see you all then. And I hope in the meantime, you'll take care of each other and stay curious.